Welcome back. Today I will be talking to you about triple integrals in two different coordinate systems. First, we're going to talk about triple integrals in cylindrical coordinates, and then we'll be talking about triple integrals in spherical coordinates. So we're going to start off looking at this definition of the cylindrical coordinate system. And it says that in the cylindrical coordinate system, a point P in R3 is represented by the ordered triple R theta Z, where R and theta are polar coordinates of the projection of P onto the xy plane, and then Z is the directed distance from the xz plane to P. Okay, and I think that the best way to really think about this is just to draw a picture. So let's draw a picture of what we've got here. First, let's draw our three-dimensional coordinate system. So here's our x, here's our y, here's our z. And let's say that we've got a point that's out here in space, but since this is three-dimensional, it can be a little bit hard to see. So let's say we're going out a certain direction, a certain amount of the x direction, then out in the y, and then out in the z. So we go out this way, over y units, and then up z units. And we've got a point here. Let's call it P. Okay. So the way that we're going to think about this point P in terms of what we're going to call cylindrical coordinates is P, well, P could be written as x0, y0, z0 in rectangular. So P is x0, y0, z0. That's one way to write P in cylindrical coordinates. But if we were thinking about it in terms of cylindrical coordinates, this is rectangular, then how would I write P? Well, remember, in the xy plane, this point down here has a polar representation, okay? And so I could think of it as I go out some distance r sub 0 through some angle from the x-axis theta sub 0. Okay, so the first thing I'm going to do is I'm going to say, in the xy plane, how do I get under that point P? In other words, if I project P straight down at 90 degrees to the xy plane, then what is its polar coordinate? Well, it would be r sub 0, theta sub 0. And then I just have, if I know the point that's directly under it, I just have to go up to my point P. Well, how high do I have to go? Well, I have to go z sub 0 up. So this is its cylindrical coordinate. Okay, so it would be represented as x0, y0, z0 in rectangular, and r sub 0, theta sub 0, z sub 0 in cylindrical. So notice that the z coordinate is the same in rectangular and cylindrical. Nothing changes in the z direction. All we're really doing is switching the xy coordinates from rectangular coordinates into polar coordinates. And in fact, that's all we're doing, is we're just switching xy's to r's and thetas. Okay? So if you understand that, we're pretty ready to do some things with cylindrical coordinates. But really quick, let's write down some conversions just so we kind of remember. So conversions. So if I want to convert from rectangular coordinates to cylindrical coordinates, something that can be helpful, so I need to remember that x is r cosine of theta, y is r sine of theta, and z is equal to, well, just z, okay? And then if I'm trying to switch back into rectangular, oftentimes things that are helpful is that r squared is x squared plus y squared. That can be helpful to me. I have that tangent of theta is equal to y divided by x, and that can also be helpful to me. So these 5 conversion formulas are going to be helpful to us as we try to do some cylindrical problems. Okay, so real quick, let's do a quick example. Let's describe the curve z equals r in cylindrical. Okay, so if I thought about this on my 3-dimensional axes, then what this is saying is give me any value for r, and that's also the value of z. Now, theta doesn't show up in this equation at all, so theta can be anything. So let's say that r is 0, then that means that z is 0. So that just gives me the origin point. And it doesn't really matter what theta is because r is 0. Now, let's say that r is 1. So let's go out 1. That means that z is 1. So when z is 1, r could be 1, and theta could be anything. So that means up here at 1, we're getting a circle of radius 1 around this point. If r is 2, then we're getting a circle of radius 2 around that point. And so on. So this isn't being drawn super well, but what we'll end up getting is a nice cone here. So this isn't the best cone I've ever drawn in my life, but maybe I'll back this up real quick. Better cone would be here's at 1, up here at 2, and so on. So we've got this cone. Now, what if r was a negative number? If r is negative, then that means that z is negative, and that means that this cone would continue down in the other direction as well, and there would be a cone underneath. Okay, so this is kind of a full cone going up and going down. Okay, so that would be the equation of z equals r. It gives me a cone. Let's try another one. So what about, let's describe r equals 1 in cylindrical. Okay, so let's draw in our axes. This is my x, my y, and my z. R equals 1 in the xy plane is just the circle of radius 1 around the origin. And z can be whatever it wants to, and theta can be whatever it wants to. So if z can be whatever it wants to, I just continue this up, and I continue this down, and I get this cylinder. So r equals 1 is just an infinite cylinder, a right circular cylinder in 3 dimensions. Okay, so we're starting to get a feel for what curves can look like in cylindrical coordinates. So now, how do I actually integrate in cylindrical. So let's think about triple integrals. In cylindrical. All right. So just like in rectangular, I can take a triple integral in cylindrical, and this is the way that it's going to be done. So let's say that I want to take a triple integral over some three-dimensional region E of some function f of x, y, z dv. Then you will have to convert this thing into cylindrical. Right now it's in rectangular. We've got x's, we've got y's, we've got z's. I'll have to convert it over into cylindrical coordinates. And remember, we integrate from a top surface to a bottom surface, from a top function to a bottom function, from a constant to a constant. We're going to do the same thing here, but here's how it's generally going to work for cylindrical. I'm going to start, the outside is going to be integral from alpha to beta, where alpha and beta are angles. Then I'm going to have the integral from h sub 1 of theta to h sub 2 of theta, where h sub 1 and h sub 2 are polar curves. So think of those as r's. And then integral from, we'll call this one u sub 1 of, well, they're going to be functions of x and y, but really we can describe that as r cosine of theta and r sine of theta, and u2 of r cosine of theta and r sine of theta. Those are surfaces that are functions of r and theta. Then I have f of x, y, z inside, but that will change to a function of r cosine theta, r sine theta, and z just stays z. And then I have to remember that if I'm switching from rectangular into cylindrical, I have this extra r that needs to go inside. So I need to write in an r. And then we need to think about, okay, so I'm going from a surface to a surface. The surface to a surface is happening in the z direction. So this is dz. Then I'm integrating from a curve to a curve, and this is r equals h1 of theta to r equals h2 of theta. A curve to a curve, that's happening in the r direction. Those are functions of theta. And then I'm integrating from a theta value to a theta value, so d theta. So this is the formula that I'm going to want to use if I'm doing a triple integral in cylindrical coordinates. All right, let's look at this first example. So this example says that a solid E lies within the cylinder x squared plus y squared equals 1, below the plane z equals 4, and above the paraboloid z equals 1 minus x squared minus y squared. The density at any point is proportional to its distance from the axis of the cylinder. So find the mass. Okay, so really mass is integrating over a density function. Okay, so what we're going to do is we're going to integrate over the region E, and what we'll be integrating is the density of that object at the point that we're integrating. So we're integrating some density function over the region E. Okay, so first let me draw you a picture to kind of set this up. So what I know is that I have some cylinder, x squared plus y squared equals 1. Okay, so let's draw this. Here's my x, y, z axes. And I've got the cylinder x squared plus y squared equals 1. X squared plus y squared equals 1 is a cylinder around the origin. So we've got this cylinder. It goes up infinitely far, down infinitely far. You get the idea. If you'd like, I could cap it up here. Okay, but it keeps going infinitely in both directions. Okay, and it says it's below the plane z equals 4. So up here I'm going to say, okay, let's say that this is 4. So we've got the plane, so we're kind of cutting the top part of this cylinder off. So we're capping it up here. So we're cutting the cylinder. So now it doesn't go above z equals 4. And then it says it's above the paraboloid z equals 1 minus x squared minus y squared. So z equals 1 minus x squared minus y squared is up at z equals 1. And then it curves downward. Okay, so it's kind of like curving. It starts up, this is z equals 1, and then it curves down and intersects. So let me write this down. This is z equals 1 minus x squared minus y squared, and that's this paraboloid right here. So what is it that I'm trying to find? I'm trying to integrate over this region that's trapped inside this cylinder, but above this paraboloid right here. Okay, so it's kind of like I took a cylinder. So if I look at this shape, it's a cylinder that's 4 high. So this part down here, this could just go. Okay, that part is not needed. So we've just got a cylinder that's 4 high, and then I'm cutting kind of a piece out of the middle. Okay, so this comes across here. So I'm cutting this little paraboloid out of the bottom of it. Okay, so it has kind of like a little bowl cut into the bottom. Okay, so now that's the region I'm integrating over. That's not the function that I'm integrating. So first, I think we are ready to set up the integral itself. Because what I want to do is I want to say, is there a top surface and is there a bottom surface? Well, the top surface is up here, this plane. That's the plane z equals 4. And is there a bottom surface? Yeah, there's a bottom surface. It's this paraboloid. And the paraboloid is z equals 1 minus x squared minus y squared. So there is a top function, I should say a top surface, and there is a bottom surface. Now, this bottom surface right now is written in rectangular. I'd like to use cylindrical. So I'm going to convert it and write it as 1 minus r squared. So I've got a top surface in cylindrical, and I've got a bottom surface in cylindrical. All right. Once I've got that, now I want to look at the region that is projected into the xy plane. But before I do, let's start out by writing what I know. I know that I have a triple integral here, and that the bottom surface I said was 1 minus r squared, and that the top surface was 4. So that's my dz. Okay, and then I want dr, and then d theta. So what do the r's range to and from? Well, if I project this region down into the xy plane, I just get a circle. What's the circle's radius? Well, in this case, this would just be the circle 1 equals x squared plus y squared. So this is a circle of radius 1. So I'm integrating from r equals 0 out to r equals 1 in all these directions. So this is going from 0 to 1. And then the thetas start at 0. And then I keep picking up thetas until I get all the way around to 2 pi. Now the last question is, this sets up that I'm integrating over that region. What is it that I'm integrating? Well, the problem said that the density at any point is proportional, so it's going to have a constant multiplied by it to make it proportional to its distance from the axis of the cylinder. The axis of the cylinder is the z-axis. And so what is its distance from the z-axis? Well, in this case, the distance from the z-axis is what we call r. Okay, so this is it being proportional from its distance from the z-axis. But then I have to remember that this is cylindrical. So I have to multiply by an additional r. Okay, so I've now set up the integral. This is the triple integral that will get me my answer. Okay, so now let me erase this picture down here and let's start working on computing this integral. All right, so first of all, I am going to just work on this inner integral. But notice this is saying integrate kr squared with respect to z. Well, kr squared with respect to z, that's just a constant. So this is just going to be the integral from 0 to 2 pi, integral from 0 to 1, of kr squared. And then when I integrate with respect to z, I'm going to pick up a z evaluated from 1 minus r squared to 4 dr d theta. All right, let's plug things in. When I do, I get integral 0 to 2 pi, integral 0 to 1 of, if I plug in 4 for z, I get 4k r squared minus, and now I want to plug in 1 minus r squared for z, and I get k r squared times 1 minus r squared dr d theta. And now I could simplify that a little bit, and I think I would like to. This is equal to the integral from 0 to 2 pi, integral 0 to 1 of, this is 4 kr squared minus 1 kr squared. So that's 3 kr squareds. And then I get minus kr squared times minus r squared, which gives me plus kr to the 4th. And I still have this dr d theta. Now I'm ready to take an antiderivative of this with respect to r. So let's do it. I still have this integral from 0 to 2 pi hanging out. And then I take the antiderivative of 3r squared with respect to 3kr squared with respect to r, and I get kr cubed. Then I need to take the antiderivative of kr to the 4th with respect to r, which is plus k over 5 r to the 5th, evaluated from 0 to 1 d theta. So now we're plugging in for r, and I get integral from 0 to 2 pi of, plug in the 1 for r, and I get k plus k over 5 minus, if I plug in 0, I just get 0, so that's it, d theta. And now I'm ready to take the derivative of that with respect to theta. Well, this is just integral from 0 to 2 pi of, this is 5k over 5 is the same as k, so this is just 6k over 5 d theta. Otherwise, if I take the antiderivative, I get 6k over 5 times theta evaluated from 0 to 2 pi. Plug in the 2 pi, and I get 12k pi over 5. And if I plug in 0, I just get 0. So the answer is 12k pi over 5. And that would be the mass of that object given that density function. Okay, so that is one example for us. Let's do one more example. So for our next example, let's evaluate the following triple integral. So I'm going to have from -2 to 2, and then integral from -4 minus x squared to √4 minus x squared of integral square root of x squared plus y squared to 2 of x squared plus y squared dz dy dx. Okay, so we could go through and start doing some work on this, but already I'm seeing that I don't like this very much. There are a lot of really nasty things in this integral, a lot of square roots, and I think that I could do better. So what I want to do is I'm going to just take this integral and I'm going to say, what really is the region that I'm integrating over? So now I need to look at this thing and determine what is the shape. Well, what this tells me is what the bottom surface is. The bottom surface here is a z equals the square root of x squared plus y squared. What is that? Well, if I squared both sides, that's z squared equals x squared plus y squared. But I know that z has to be positive. So what that is if I look at my axes here, x, y, and z, then z squared equals x squared plus y squared is a nice cone. So we've got the upper half of a cone. That's the bottom surface. The top surface is up here, and that's z is equal to 2. So if I go up 1, 2, at 2, I cut this thing off. Okay, so I'm cutting it with a plane right here. So this becomes the top of my shape. So this is just a truncated cone. So if I wanted to redraw it really quick, maybe I'll erase real quick here. So draw it a little nicer now that we know what it looks like. So I just have this cone that goes up 2 units. Okay, and this is z equals 2. Okay, so that is what? The cone is the bottom part of my function is the cone itself, and the top of the function is the top surface of this shape is the plane z equals 2. Okay, so now I need to look at, okay, but what is the projection into the xy plane? If I look at this thing projected down into the xy plane, what would it look like? Okay, let me erase a little bit here. I want it to just go down here. So it would look something like just a circle down here, right? Okay, so what is this circle in the xy plane? Well, there's a bottom function and a top function. If this is x, this is y. I've got a top function and I've got a bottom function, which just happen to be y equals negative square root of 4 minus x squared and y equals square root of 4 minus x squared. So that's my top function and my bottom function. And then in the x direction, I'm going from negative 2 to 2. So it's all set up. So this is exactly what my shape is. It's this cone that is cut off on top at z equals 2. Knowing that, can I rewrite this thing as a triple integral in cylindrical that is going to be a little bit nicer to integrate than this beast? Okay, so now that I know what this thing looks like, can I make it better? I think so. Okay, so let me start working on this. So I'm going to say that this guy is equal to integral, integral, integral. And now I need to start thinking of these things in terms of cylindrical. Certainly the top function up here, or the top surface, I guess I should say, is z equals 2. That doesn't change. The bottom is the cone, but the cone, instead of writing it as z equals square root of x squared plus y squared, I could write it as z equals the square root of r squared, which is just r. So it's just z equals r. So down here, I'm just going to have an r. Okay. And now what I'm going to do is down here, this is just saying r goes from 0 out to 2, and theta goes from 0 to, goes all the way around, and I get back to 2 pi. So this is going from 0 to 2, 0 to 2 pi. And look how much nicer the numbers are now that I'm integrating with respect to. Instead of all these square roots of x squared plus y squared and square root of 4 minus x squared, I have like 0, 2, 0, 2 pi. Much better. Now I need to figure out, and then back here, let me erase a little more. I'm going to erase the picture now. We don't need it. I know that what goes back at the end here is I'm going to want dz, dr, d theta, which is almost always what I'm going to want to have the order be when I'm doing cylindrical. Okay? Now, what goes inside? Well, x squared plus y squared goes inside, but what's x squared plus y squared? Well, that's r squared. And then I have to remember that I changed this to cylindrical. And any time that I change from rectangular to cylindrical, I'm going to have to multiply by an additional r. So really what's inside is r cubed. All right, now we're ready to actually take this integral. So let's do it. I've got integral 0 to 2 pi, integral 0 to 2. I'm going to take the antiderivative of r cubed with respect to z, and I'll just get r cubed z evaluated from r to 2 dr d theta. Let's plug it in. I get integral from 0 to 2 pi, integral from 0 to 2 of, if I plug in the 2, I get, for z, I get 2r cubed. And if I plug in the r for z, I get r to the 4th, all of that dr d theta. Now I'm ready to take the antiderivative with respect to r, and I get integral from 0 to 2 pi of, if I take the antiderivative, I'll get 1/2 r to the 4th minus 1/5 r to the 5th evaluated from 0 to 2 d theta. Okay, let's plug in the 2 and the 0. I get integral from 0 to 2 pi. If I plug in 2, I get 2 to the 4th, which is 16 divided by 2 is 8. And then if I plug in 2 for r to the 5th, I get, let's see, what would that be? That would be 32 divided by 5, so minus 32 fifths d theta. Okay, we're almost done here. 8 is how many fifths? I suppose that 8 is 40 fifths. So 40 minus 32 fifths would be 8 fifths. So I really have integral 0 to 2 pi of 8 fifths d theta. Let's complete this on the next page. So I can take the antiderivative and I just get 8 fifths theta evaluated from 0 to 2 pi. Plug in the 2 pi and I get 16 pi over 5. And if I plug in 0, I get 0. So I just end up with 16 pi over 5 as my answer. Okay, so that gives you a good handle on cylindrical. You're certainly ready to try some problems on cylindrical, and now we need to start talking about spherical coordinates. Okay, now let's talk about the definition of spherical coordinates. And we've dealt with polar, we've dealt now with cylindrical, and now let's talk about spherical, which is a little bit different. So in spherical coordinates, let's say you have a point P. So let's look at this point P out here in this three-dimensional coordinate system. Then the way that I could describe that point P is with three quantities. The first one I'm going to call rho. This is theta, and this is phi. Okay, so rho is going to be the distance right here. It says it's the distance between O and P. So this distance right here I'm going to call rho. Okay, theta is the angle of that point, the projection of that point into the xy plane. So this is my x-axis. So this angle right here, I call that theta. And then phi is the angle between the positive z-axis down to the line segment OP. So this is what I call phi. And given those three quantities, I can always describe any point with a rho, a theta, and a phi. All right? Now, there are a couple things that you need to note here. The first is that rho is always going to be greater than or equal to 0. In polar coordinates and in cylindrical coordinates, we did not make this extra condition on r. We said that r could be positive or negative. In spherical coordinates, we're going to say that rho has to be a non-negative number. Second thing is that 0 is always going to be less than or equal to phi, which is always going to be less than or equal to pi. And it's very important that you notice that this is pi and not 2 pi. Because if you're taking an angle down to a line segment anywhere from the z-axis, the furthest you could get away from the z-axis is the negative z-axis. And what's the angle all the way down to the negative z-axis? It's pi. So the biggest that phi could ever be is pi, not 2 pi. Theta, on the other hand, can go from 0 all the way around to 2 pi, that's fine. So theta can live in between 0 and 2 pi, but phi is restricted to being between 0 and pi specifically. Okay, let me talk about a few equations that are simple equations in spherical. And maybe the most simple thing is we could say that rho is equal to a constant. If rho is equal to a constant, that says take all things where the distance from the origin is c. Well, everything where the distance from the origin is c is just a sphere centered at the origin of radius c. So we would just get a sphere centered at the origin of radius c. Okay, so that's rho is equal to c. What if I had theta is equal to a constant? If we have theta equals c, then I have a constant value for theta. This is my angle theta. And then what would happen is I could have any points above or below that angle theta. So that would give me basically a half plane. Remember that rho is positive. So I don't get the back half of the plane, just the front half of this plane. So I'd get this whole half plane over here. Okay, so that's theta is equal to a constant. What if you had that phi is equal to a constant? Okay, let's draw that one. So phi is an angle down from the positive z-axis. And let's say that that angle down from z was constant. And then what I would end up doing is saying, okay, well, that could be any any rho. So that means that whole ray would be on. And then it could be any theta. So now take that ray and spin it around the z-axis, and you'd get the similar ray on this side, and then spinning that around at that angle phi, you'd get a nice half cone. Just the top half of the cone. You would not get the cone that would be below the z-axis. Because again, rho needs to be a positive value. Okay, so you'd get a half cone. Very interesting. Okay, so just like we had conversions from rectangular to cylindrical, we also need conversions from rectangular to spherical. So converting from rectangular to spherical. So here are going to be my equations. Now, these are a little bit more complicated. They're just all trigonometry at the end of the day. They can all be shown just using triangles. But I'm just going to write them down for now, and I would challenge you to think about these a little bit and see, do you believe what I'm saying here? That x is equal to rho sine phi cosine theta. That y is equal to rho sine phi sine theta. And that z is equal to rho cosine of phi. Okay. Finally, we also get that x squared plus y squared plus z squared is the same thing as rho squared. Okay, so these four conversion formulas should be helpful to us. Okay, let's do an example. So let's plot the spherical point to pi over 4, pi over 3, and give its rectangular coordinates. Okay. So first of all, let's plot that. So let's draw our three-dimensional axes. Here's x, here's y, here's z. So what pi over 4 tells me, that's my theta. And so pi over 4 says go through an angle of pi over 4, which would look about like this. And then phi says drop down an angle of pi over 3 in that direction. So that would kind of drop over here. And then it says on that line in this direction, so this is straight over this in the xy plane, go out 2 units, 1, 2, and make a dot. Okay, so this is directly above some point over here. This is an angle of pi over 4, and this is an angle of pi over 3. And we get our point right here. Okay, so that's plotting the point. Now we want to give its rectangular coordinates. Okay, to do that, we need to use our formulas. We know that x is equal to rho sine phi cosine theta. In other words, x is equal to rho, which is 2, sine phi, so sine of pi over 3, cosine of theta, which is pi over 4. So x is equal to 2. Sine of pi over 3 is root 3 over 2. And cosine of pi over 4 is root 2 over 2. So some 2's cancel, and I get that x is equal to the square root of 6 over 2. Okay, now I need y, so that's my x value. Y, let's go over here, is equal to rho sine phi sine theta. So this is just the same, 2 sine phi, which is pi over 3, sine theta, which is pi over 4. So sine of pi over 4 is the same as cosine of pi over 4. It's root 2 over 2. So everything's the same here, and I get root 6 over 2 for y. Okay, and then z is rho cosine of phi, which is 2 cosine of pi over 3. Pi over 3 is 1/2, so this is 2 times 1/2, otherwise known as 1. So if I wanted to give its rectangular coordinates, the rectangular coordinates of that point are root 6 over 2, root 6 over 2, 1. And that is the rectangular coordinates of that point. Sound good? Okay. Let's talk about doing triple integrals in spherical coordinates. Okay. So if I want to do a triple integral in spherical, this is the way that it's going to go. I could go through a whole Riemann sum explanation here again. I'm not going to in this case. What I'm going to do is I'm just going to give you the formula for triple integrals in spherical. So if you're trying to take a triple integral over a region E of f of x, y, z dv, then this is going to be equal to the integral from c to d, integral from alpha to beta, integral from a to b, of f of, well, x, but x is rho sine phi cosine theta, then rho sine phi sine theta, and then finally rho cosine phi. And then just like in cylindrical we had to add an extra r, in this case we need to add an extra rho squared sine phi, and then this is going to typically go d rho d theta d phi. Okay, so it's very important that we remember to add this rho squared sine theta in after converting into spherical coordinates. Okay, let's try an example and see how this goes. So an example, let's evaluate the triple integral over b of e to the x squared plus y squared plus z squared, all of that's in the exponent, to the 3/2 power dv, where b is the unit ball. In other words, the ball of radius 1 centered at the origin. Okay, so if we're working with the ball of radius 1 centered at the origin, so here's my unit ball. Then I want to know, first of all, here's my triple integral, and at the end I'm going to say this is d rho d theta d phi, and I'm going to say, what does rho range between? Well, the points inside the ball range between rho equals 0 and all the way out to rho equals 1 in any direction between 0 and 1. So this is going to range from 0 to 1. What do the thetas range from? Well, this is theta equals 0, and it goes all the way through all of the angles until it gets back to 2 pi. So theta is ranging from 0 to 2 pi. And then phi starts at 0 is up, and then it goes all the way until it gets to the bottom, which is from 0 to pi. Okay, not 0 to 2 pi, because it doesn't need to come up. Because when you spin this kind of half circle around in all of theta, from 0 to 2 pi, it generates the entire unit ball. So you don't need to keep going up through the angles between pi and 2 pi for phi. You only need from 0 to pi. Okay, now what goes in the middle? Well, we've got e to the x squared plus y squared plus z squared, but x squared plus y squared plus z squared is otherwise known as rho squared. So this is rho squared to the 3 halves. And then I need to add in this additional factor because I'm switching to spherical. So I need to add in rho squared times sine of phi. And now I am ready to take my integral. Okay, so let's do the integral first. So this is going to be integral from 0 to pi, integral from 0 to 2 pi of, okay, this one, to take this inner integral, I really should do, maybe I should even simplify it a little bit first, because I could write this as the integral from 0 to 1 of e to the rho cubed, right? Because rho squared to the 3 halves is the same as rho cubed times rho squared sine phi d rho d theta d phi. Okay, so now what I could do is I could use a u substitution here. So if I let u be equal to rho cubed, then du would be 3 rho squared d rho. Correct? So now I could rewrite this as the integral from 0 to pi. Let's see, I guess I need a 3 in there to make this substitution. So I'll put in a 3, which means on the outside I could put in a 1/3. So I need a 1/3, integral from 0 to pi, integral from 0 to 2 pi. And then I'm going to make a substitution, and it's going to give me e to the u sine phi du d theta d phi. And now I can take the antiderivative. Now I should change the limits of integration. If if rho is 0, then u is 0. And if rho is 1, then u is 1. So now I can take an antiderivative. I still have the 1/3 on the outside. 0 to pi, integral 0 to 2 pi. Take an antiderivative of e to the u sine of phi with respect to u, and I get e to the u sine phi evaluated from 0 to 1 d theta d phi. Okay, so now I'm ready to plug that in. So let's go ahead and plug it in. And if I do, I get the following. I get the 1/3 is still there. I have the integral from 0 to pi, integral 0 to 2 pi, and then I plug in the 1, and when I plug in 1, I get e sine phi, and then minus plug in 0, but if I plug in 0, I get e to the 0, which is 1, so I just get sine phi d theta d phi. Now, if I wanted to, I could simplify that a little bit. Notice that each of these has a sine of phi, so I could factor out the sine phi, and I could write it this way. I could write it 1/3. If I factor out a sine of phi in here, I get an e minus 1 sine phi. But e minus 1 is just a constant, so I could take it out of the integral. So I have an e minus 1, integral 0 to pi, integral 0 to 2 pi. And now what's left inside is sine phi d theta d phi. Now I'm going to take the antiderivative with respect to theta, not with respect to phi. So the antiderivative of sine of phi is just sine phi times theta. So I get 1/3 e minus 1, integral from 0 to pi. Antiderivative now of sine of phi is sine phi times theta, evaluated from 0 to 2 pi d phi, which is equal to, this is times, by the way, so I get 1/3 e minus 1, integral 0 to pi. If I plug in the 2 pi, I get 2 pi times sine phi. And if I plug in 0, I get 0. So this is just d phi. Okay. By the way, the 2 pi now, if I wanted to, the 2 pi could come out. So I get 2 pi over 3 times e minus 1, integral 0 to pi of sine phi d phi. So this is 2 pi over 3 times e minus 1. The antiderivative of sine of phi is negative cosine of phi, evaluated from 0 to pi. Okay, let me erase a little bit up here. I'll just finish this off. So, finishing this off, I get, this is equal to 2 pi over 3 times e minus 1. If I plug in the pi, I get negative cosine of pi. But cosine of pi is negative 1. So I get minus minus 1. Minus, and then I plug in the 0, I get minus cosine of 0. So minus cosine of 0, which is 1. So what is that? This is 1 plus 1. So that's just 2. So I get 4 pi over 3 times e minus 1. And that's my answer. Okay, very cool. So that's your first triple integral in spherical coordinates. Let's try one more of these for practice, and then it's time to try some homework over cylindrical and spherical. So last example here. Let's use spherical coordinates to find the volume of the solid that lies above the cone z is equal to the square root of x squared plus y squared, and below the sphere x squared plus y squared plus z squared is equal to z. Okay. So what we have here is we have, first of all, a cone. Okay, this cone is going to look something like this. Okay, so we've got this cone. And then we have a sphere. Okay, now what does this sphere look like? Well, if I rewrote this in spherical, then I would get the following. I'd get that rho squared is equal to z, but z is what? It's rho times cosine of phi. I could divide both sides by rho, and I would get that rho is equal to cosine of phi. All right, so what exactly does this thing look like? Well, we're already told that it's a sphere, and we know that it's equal to cosine of whatever my angle is off of. So over here, it's 0 here at what? When phi is 0, rho is also 0. So that would give me here. And when phi is I'm sorry. When phi is 0, rho is 1. So that would put it out here at 1. Okay, so that's 1 unit out. And then it kind of goes through how far can phi go? Well, it can go all the way to pi. But cosine of pi would be -1, and I know that rho can't be negative. So as far as it could go is pi over 2. And at pi over 2, we'd have 0. So this thing kind of goes from 1 to 0 as we make an arc from phi equals 0 to phi equals pi over 2. It does that in all directions. So what it's saying is it's below this sphere and it's above this cone. This may not be the prettiest picture I've ever drawn, so let me redraw it so that it's a little more clear. Okay. So what this is saying is I've got a sphere that is the top of this. So I've got a cone on the bottom. But then that cone is kind of topped by the top of a sphere. So up here, I've got a sphere on top. So you might think this kind of looks like an ice cream cone. Okay, so you've got the cone part down here, and then you've got kind of the ice cream up here on top, right? Okay, so this is kind of an ice cream cone shape. And the question is, what's the volume? Okay, so what are we supposed to integrate if we're just finding the volume? Well, the best way to do this is we just integrate the function 1. In other words, just give it the density of this thing, a density of 1 everywhere, and that will just give you the volume of the shape. So we're just integrating 1 except for that extra factor that I have to put in because I'm switching this into spherical. So how do I integrate this thing? Well, I've got to think about, okay, is there something on top and is there something on the bottom? Yeah, it's kind of like the ice cream's on top and the cone is on the bottom, right? But I don't know if that's good enough for me, because really what I need to think about first is how far does rho extend? Well, it starts at 0 and it extends always out. If I'm going array from the origin, it always goes out to the ice cream. And how far out is the ice cream, so to speak? Well, it depends. It's on that function, right? What is the function that's out there? It's always the ice cream cone, though. Well, we said that that ice cream cone could be represented, or the ice cream part is rho is equal to cosine of phi. So we're starting at rho equals 0, and we're going out to cosine of phi. Okay, so the inner integral, we're going from 0 to cosine of phi. And I know what's inside here is just 1 times that conversion of rho squared sine phi. So that's the only thing that's going to be inside my integral to compute volume. And then this, first of all, I said that this is d rho. All right, now I need to decide which to do next. Do I want to take theta or phi? It doesn't really matter. Let's say we take theta. Well, theta starts at 0, and we pick stuff up all the way around the circle. So we go from 0 to 2 pi. Then I need to say, well, what about phi? Phi starts at 0, and we start taking stuff until we get to the edge of the cone, and then we stop. So this starts at phi equals 0, and we keep picking up volume until we get to this angle. Well, what's that angle? That's the angle phi equals pi over 4. Okay? Because we know that that's at a 45-degree angle. So we're going from 0 to pi over 4. So now this thing is set up and completely ready to integrate. Let's do it, and then we'll be ready for some homework. Okay, so let me move to a different page. So I want to integrate, first of all, that rho squared sine phi with respect to rho. So what I get is I get integral 0 to pi over 4, integral 0 to 2 pi of, it's going to be 1/3 rho cubed sine phi evaluated from 0 to cosine of phi. Okay, so we get, and then this is going to be d theta d phi, and we're plugging in for rho. So what we get is integral 0 pi over 4, integral 0 to 2 pi of, plug in the cosine of phi, and I get 1/3 cosine cubed phi sine phi minus, if I plug in 0 for phi, I get 0 d theta d phi. All right, so that 0 is just gone. And now I want to integrate this guy with respect to theta, but that's just a constant with respect to theta. So I just get integral from 0 to pi over 4 of 1/3 cosine cubed phi sine phi times theta evaluated from 0 to 2 pi d phi, which is integral from 0 to pi over 4 of, I could pull the 1/3 out if I want to. Let's do it. And then I get 2 pi times cosine cubed phi sine phi minus 0, so that's it, d phi. I could pull that 2 pi out of the integral if I wanted to. I do. So I get 2 pi over 3 integral 0 to pi over 4 of cosine cubed phi sine phi d phi. Okay, now this is just a nice u substitution. I want to u substitute u is equal to cosine of phi, and that means that du would be negative sine of phi d phi. So I need a negative in here, so I need a negative out here. So this is going to give me negative 2 pi over 3 integral of, now this will be u cubed du, and now I need to change the limits of integration. So if phi is 0, cosine of 0 is 1. And if phi is pi over 4, cosine of pi over 4 is root 2 over 2. So now I'm ready to take an antiderivative with respect to u, and I get negative 2 pi over 3 times, this is 1/4 u to the 4th, evaluated from 1 to root 2 over 2. Okay, we're almost done. Let me erase some of this up here, and we will finish up. Okay, so what do we have? This is equal to, I could bring the 4 out side of that bracket, and I could write this as minus, well, the 2 and the 4 cancel and give me a 2, so I get minus pi over 6 times. So if I plug in the root 2 over 2 into the u to the 4th, I get 4 over 8. Let's see. Let me think about that for a second. So I get root 2 over 2 to the 4th. Let's just write it that way. Root 2 over 2 to the 4th minus 1 to the 4th. Okay. What is that? This is minus pi over 6 times. Square root of 2 to the 4th is 2 squared, which is 4. And 2 to the 4th is 4 squared, which is 16. So this is 4 over 16 minus 1. Okay, well, 4 over 16 is otherwise known as a 4th. So this is minus pi over 6. And I've got 1/4 minus 1, which is negative 3/4. Minus times minus is a positive, and I've got a 3 pi on top, and I've got a 24 on the bottom. But 3 and 24 cancel, and that just gives me pi over 8. And that's my answer. Okay, so we were able to do this example fairly straightforward. The hardest part, again, of these problems is setting it up. So really get comfortable, and you might actually have to even watch this a couple times to get a good feeling for what's going on with spherical. Okay, what's the theta, what's the phi, what's the rho, what am I talking about here, so that you can really set up these triple integrals. Once you can set them up, the integration is just pretty straightforward. The one other little tip I would give is make sure that you know what a phi looks like and what a theta looks like. Don't draw them close to each other so that you get them mixed up. It's easy to do, and so just make sure you're drawing your thetas very differently from your phis so that you don't mix the two up.